Hey YouTube, the Mafia306 here with video lesson 2.2 in the Let's Learn Calculus series. I'm sorry that I haven't uploaded any videos lately. I think the last one was on Christmas Day. And the reason is because I am at my mother's fiance's house and I left my whiteboard at her house. So after waiting a while, I said, what the heck, and you get my raw, unedited notes for this video, because I need to really get these videos rolling, in case some of you might be taking calculus this semester coming up. I apologize if you can't read these. I wrote them as big and as dark as I theoretically could without using an extremely profligate amount of paper. So, without further ado, let's just go ahead and get started. This section is on calculating limits using the limit laws. And we start off by saying that suppose that c is a constant, and the limit of f of x as x approaches a, and the limit of g of x as x approaches a both exist. Then we have a multitude of laws that follow. Law 1 can best be summed up as saying that the limit of the sum equals the sum of the limits. The second law, the limit of a difference equals the difference of the limits. The third law, the limit of a constant times a function is equal to the constant times the limit of the function. The fourth one, the limit of a product equals the product of the limits. And the fifth one, the limit of the quotient is the quotient of the limits, provided that the limit of the denominator is not equal to 0. And we also have some other limit laws that follow. The limit of a function raised to the nth power is equal to the limit of the function raised to the nth power, all under the power sign, where n is a positive integer. And now this is something that I actually don't know, and if anybody knows why this is, I would really appreciate your input, because to be completely honest, I don't know why this is. Does n necessarily have to be a positive integer? In other words, can n be negative? Or can n be a rational number like 2/3? Or could it even be irrational, like square root of 2? I mean, does anybody know this? Because I would really like your input on that. Anyway, moving on. The limit of a constant equals the constant, and the limit of x as x approaches a equals a. And we also have that the limit of x to the n equals a to the n, where n is a positive integer. There's a couple more here. The limit of the nth root, get it so you can see it. There we go. The limit of the nth root of f of x equals the nth root of the limit of f of x, where n is a positive integer, and the limit as x approaches a of the nth root of x equals the nth root of a, where n is again a positive integer. So I've got just a couple of example problems here. Here we have a graph of two functions. F of x is this curved function here, and g of x is this piecewise defined linear function here. So the first one is the limit as x approaches -2 of f of x plus 5g of x. So we can start off, and we see from the graph that the limit as x approaches -2 of f of x equals 1. That's here. Notice that even though f of -2 equals 2, it doesn't matter what the value is at x equals -2. What only matters is the value of f of x as x approaches -2 from the left and the right. So we get 1. And we get that the limit of g of x as x approaches -2 equals -1. That's right here. And then we just break it up using the limit laws. So here we break it up as the limit of the sum equals the sum of the limits. That's by law 1. And then this is equal to, by law 3, as just the limit of a constant times a function equals the constant times the limit of the function, and then we just plug in and we get -4, and that's just from the graphs, and we get -4. So now we come up to the direct substitution property, which says that if f is a polynomial and a is in the domain of f, and that's very important, a must be in the domain of f in order to be able to use this property, then the limit as x approaches a of f of x equals f of a. In other words, you just plug in the value x equals a into the function. And functions that have this direct substitution property for all values of x, from -infinity to +infinity, are called continuous functions. And these functions will be studied in a later section, probably lesson 2.4, if I had to guess. Yeah, probably 2.4. But for now, just know that functions with this property are called continuous. So as another example, we have find the limit as x approaches 1 of x squared minus 1 over x minus 1. And you saw that we did this in the previous lesson, but we can do it easier here. But first, note that we can't use the direct substitution property because f of x is undefined at x equals 1. If you plug in x equals 1 into the function, you get 0 for the denominator. So 0 is not in the domain of f, so we cannot use the direct substitution property. But we can do some preliminary algebra, and what we do is we factor the numerator, and then we get x minus 1 to cancel. So really this is equal to the limit as x approaches 1 of x plus 1. And now x equals 1 is in the domain of this polynomial, so we apply the direct substitution property, and we get 1 plus 1, which is equal to 2. Now we have a couple of theorems that arise, and it's the limit of f of x as x approaches a is equal to L, and this here just means if and only if the limit as x approaches a from the left of f of x equals L, and the limit of f of x as x approaches a from the right is equal to L also. So in other words, the left and the right limits have to be equal to each other, and then the limit as x approaches a is equal to that value as well. And we also have theorem 2, if f of x is less than or equal to g of x when x is near a, except possibly at a itself, and the limits of f and g both exist as x approaches a, then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. And that follows just directly from the direct substitution property and from the plugging into the polynomial and the difference property. So here we have another example. Prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So first we look at the right hand limit, and we have the limit as x approaches 0 from the right is equal to x over x, since for positive values of x, absolute value of x is equal to x. So we get x over x equals the limit as x approaches 0 from the right of 1, which is just equal to 1. Remember, we had that the limit of a constant is just equal to the constant itself. Now, if we look at the left side limit as x approaches 0 from the left, sorry about that, of the absolute value of x over x. Now, for negative values of x, the absolute value of x equals negative x. So we get the limit as x approaches 0 from the left of negative x over x, which is equal to the limit as x approaches 0 from the left of negative 1, which is equal to negative 1. So we get that the left-hand limit, which is negative 1, is not equal to the right-hand limit, which is 1. So therefore, the limit as x approaches 0 does not exist. And our last theorem here is called the squeeze theorem, which says that if f of x is less than or equal to g of x is less than or equal to h of x, when x is near a, except possibly at a itself, and the limit of f of x as x approaches a is equal to L, and the limit of h of x as x approaches a is equal to L, then we have that the limit as x approaches a of g of x has to equal L. And I have one last example that sort of uses this and shows this. Here we want to show that the limit as x approaches 0 of x squared sine 1 over x equals 0. And first off, we note that we cannot use the product rule here that says that the limit of the product equals the product of the limits, because the second limit is undefined. The limit as x approaches 0 of sine 1 over x is undefined. So we can't use that property. So here we have the functions graphed. This one here in the middle is our function, x squared sine 1 over x. And we see that it's bounded on the top by y equals x squared, and on the bottom by y equals negative x squared. So we have that negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. So we have the limit, we know that the limit as x approaches 0 of x squared equals 0, and the limit as x approaches 0 of negative x squared equals 0. So we take f of x equals negative x squared, g of x equals x squared sine 1 over x, and h of x equals positive x squared. We take those functions in the squeeze theorem, and then we have, thus by the squeeze theorem, we have that the limit as x approaches 0 of x squared sine 1 over x equals 0. And you're done. So I know that that's a lot of limit laws, but these will allow you to, almost in a nearly foolproof method, allow you to find the limit of just about any function that you can think of. The only exceptions are really the only exception is if you're taking a limit as x approaches infinity or negative infinity, or if you have a quotient and you get, when you get the limits, you get 0 over 0. Those are really the only two possibilities in which these rules will not work. So go out there, calculate limits, practice them, and just to kind of show you where we're going, or not even really to show you, just to kind of tell you where we're going with this, we're going to talk about, we're going to do a formal definition of limits. So far we've only sort of given an informal definition of limits, such as, you know, we know that the limit is a certain value because we can take x arbitrarily close to this other value. But none of that is really concrete, and mathematicians really like concrete things. So I guess we'll formally define limits using the delta epsilon definitions, if you've heard of that, in the next lesson, and then we'll talk about continuity, and we'll talk about limits at infinity, I think, and then we'll see where we're eventually going here is differential calculus, which deals with derivatives. And when we first define derivatives, we'll define them as limits. So that's why we're going through all of this. So I hope you guys stay tuned, and I will hopefully have up the next lesson in the next couple of days. So thanks for watching. If you have any questions, feel free to leave a comment or a message to me on here, and I'll see you all next time.